Hello everybody. I today wanted to give you some notes on ionic compounds. So we are going to move into lesson 6. Please make sure you're reading and understanding lesson 6 of the textbook, Unit 2, Lesson 6, which is all about chemical bonding. We've talked about elements and compounds, physical and chemical properties and characteristics. We have talked a lot about the atom, then we've talked a lot about the periodic table. Now we need to take all this to put it together and start putting these things together and start making actual things, actual chemicals. All we've done is talk about the elements. Now we need to take these elements and put them together and make stuff. So the first kind of bonding that I want you to know about is ionic bonding. Ionic bonds are when electrons are transferred. Also notice, ion, we've said for a while, is an atom with a charge. So, the fact that these atoms have charges is because electrons have been transferred. And what almost always happens is they get transferred from a metal to a nonmetal. So, let's do a quick example and show you exactly why this is happening. Let's say we had a bond between calcium and chlorine. If we did a Bohr model for calcium, find a periodic table, you find out that calcium has 20 protons. You find out chlorine has 17 protons. If I asked you to do the... Now notice, I haven't said anything about neutrons. Neutrons don't matter because those only tell you the isotope. If we did the Bohr model for calcium, it would have energy levels of 2, 8, 8, and 2. Chlorine would have energy levels of 2, 8, and 7. Alright? But there's something very important that is both in ionic bonds and the next kind of bond we're going to talk about. And it is super important. It's called the Octet Rule. And the Octet Rule, oct, should tell you exactly what you should already expect, and that is 8. Almost everything wants to have 8. There are, of course, some exceptions to that. Some things only need 2, and it's more complicated than this. But for the most part, there should only, or most things want to have 8 electrons. So how can we get calcium to only have 8? Well, it could either lose 2, and this becomes its last energy level, or it could gain 6. Or actually more than that, because it's 2, 8, 8, 18, but it's even more complicated than that. It's much easier for it to lose these 2. So let's just have these 2 electrons go away. If those 2 electrons go away, that now is our outer energy level. Now if you count, you'll notice that this now has more protons than it does electrons, and this becomes a positive 2 charge. Well, those electrons can't just disappear. Those electrons have to go somewhere. So where do those 2 electrons go? Well, one of them could come here. And now this chlorine has 8 electrons in its last energy level, but now it has more electrons than it does protons. This becomes negatively charged. But we still have one more electron that left here, and where could it go? The answer is another chlorine. Because if we have a chlorine, and what I'm drawing here will become known as a Lewis dot structure, Notice I don't need these inner energy levels. All I need to know is how many are in the last energy level. And if I draw 7 there, and then say, okay, another one came here, now that has 8, and we have yet another chlorine that has a -1 charge. So you have, watch, you have calcium and 2 chlorines. This is the only corner we've never put a number in. We've put atomic number in this corner, mass number in this corner, charge in this corner. We've never used the lower right corner. Now we will, because that's where we'll put the subscript that tells us how many of these we have. So calcium chloride, CaCl2. That is why an ionic bond forms, because these electrons are transferred from the metal to the nonmetal. That makes the metal positive, the nonmetal negative, and we want, almost everything wants to have 8 in their last energy level, and in doing so, calcium's happy, 2 chlorines are now happy, and we get this chemical called calcium chloride. Please, please, please know, memorize, and it's not even memorize, just understand that our valence electrons, how many electrons are in the outer energy level, is 1 for this column, 2 for this column. All of the transition metals and inner transition metals are 1 or 2. I have to tell you what those are. But then the rest of these, 3, 4, 5, 6, 7, and 8. And we just said by the octet rule that things want to have 8, the noble gases do, that's why they don't react. Of course, our exception here, helium only has 2 because it only has 2 electrons. So 1, 2, 3, 4, 5, 6, 7, 8 as you go across the periodic table. So, I just gave you a deeper understanding of what's going on here. But when it really comes down to it, I'm just going to give you a metal, I'm going to give you a non-metal, and you're going to tell me what the formula is for it. And then, I've even given you a little cheat sheet to do this. Let's do some of these, or let's do a few examples. Let's do what I just said. Or let's actually start with something a little bit, I would call less complicated. I will always give you a metal with a positive charge. I will always give you a non-metal with a negative charge. Now, you have 3 questions. You'll always answer the first one. You may go to the second one, but if you go to the second one, you're automatically going to go to the third. So you might stop after the first one, but if you make it to the second one, you're going to go to the third. So let's do this. Calcium and oxygen. +1, negative, or +2, -2. Because of that, do the charges have the same number? For example, +2, -2 as their superscripts. Do you have a +2 and a -2? Are these numbers the same? And the answer is yes, they are. What do? You drop the charges and you squeeze everything together. This is simply CaO. That's all you got to do. Just squeeze the stuff together. You'll notice that our example here is sodium and chlorine. Do they have the same number in their charges? Yes. Take the charges off, squeeze everything together, you're done. Another problem would be something like titanium with a +4 charge and oxygen with a -2 charge. Okay? Do the charges have the same number? 4 and 2? No, they don't. Well, if they don't, then you go to the second one. Can the charges be simplified? The only time you will ever say yes to this question is if you have +6 -3, +6 -2, and +4 -2. Get these on this paper. This handout I will let you use on the quiz. You obviously can use it on the homeworks, But if you know that those are the only 3 times you'll ever say yes to this question, then you'll be in much better shape. So then, we've said yes, reduce them as a fraction. So what I mean by that is 4 over 2, or you could even flip that, 2 over 4. Can that be reduced as a fraction? And the answer is yes, they can, to 2 and 1. So now what we do here is, I call it drop and flip. We are dropping these numbers, we're not dropping the charges, so the x and the y, instead of superscripts, now become subscripts, and then we flip them to the other element. So what I like to do, and let's just show this as it is, as we have it here, a to the plus x, b to the negative y. What I always do is I say a to this, b to this. And that is why we get a, y, b, x. But don't ever write the number 1. We never write the number 1. So let's finish our example here. We've already reduced it, so what's the formula? It is ti, but we don't write the number 1, o, and what number goes after the o? 2. Titanium oxide, TiO2. Let's do one more example. Let's look at the periodic table to find one to do. Let's do magnesium right here. So I know that has 2 valence electrons. Because it has 2 valence electrons that want to leave, it's probably going to become a positive 2. And let's just pick phosphorus. Now we know that phosphorus has 1, 2, 3, 4, 5 valence electrons. It's a nonmetal. It's going to want to gain electrons and get to 8. So I know phosphorus is going to have a negative 3 charge. So I go back. Let's go back to our flow chart. We are going to do magnesium with a plus 2 charge. I know magnesium has a plus 2 charge. We're going to do phosphorus because it has a negative 3. And you can go back and look at Bohr models and figure out exactly why these are going to have a plus 2 and a minus 3. But all you need to know is flowchart, flowchart, flowchart for this homework. Do the charges have the same number? For example, plus 2, minus 2. Well, we got a 2 and a 3. The answer is no. Can the charges be simplified? Do we have a plus 6, plus 4? No. Those are the only times you'll ever say yes to that question. And if you do, all you do is reduce it before you go to step 3. So they can't be simplified, so now what we do is drop and flip. We're going to drop these numbers down, so instead of superscripts, they become subscripts, and then we flip them to the other thing. So, if we simply drop them, but then we flip them, that becomes our answer, Mg3P2. But what I like to think is Mg, put that number behind it, P, put that number behind it. And that's exactly why we do that. Now, that's all you need to know in order to do the homework. If you can see why we are doing that and just simply use this flow chart, you can do the homework. And I will be handing out the homework when you get to class on Monday or Tuesday, depending on when we actually have school. Just use the flow chart and ask me questions if you don't understand why we're doing this. You can stop the notes if you understand what this is, but I want to go into just a little bit deeper detail and explain why that just happened. First, as I just said, if we go and look at the periodic table, magnesium has 2 valence electrons. Phosphorus has 5 because of the column it's in, because of the group it's in. So magnesium, we just said has 2 valence electrons. We said phosphorus has 5. Now if you really need to see it, and you really don't believe me, magnesium has 12, phosphorus has 15. Magnesium has 12, phosphorus has 15 protons. So our energy levels would be 2, 8, 2. That's why we know it has 2 valence electrons, right there. If those 2 valence electrons go away, its new energy level will be 8. Okay, phosphorus has 2, 8, and 5. If we get 3 more electrons, then this will have 8. That's giving away electrons. That needs electrons, so it's a perfect relationship. But we don't need to draw all of these. We don't need to draw all these energy levels. We can just draw these dots like this. So we know that these 2 electrons are going to go away. Boom, gone. Well, they can come over here to this phosphorus. But this phosphorus doesn't have 8. So where can it get more? It can get more from another magnesium that has 2 valence electrons. So let's change color. That one's going to leave, and it's going to come here. Okay, now that phosphorus has 8. But that magnesium still has an electron that needs to go away. So we need another phosphorus that starts with 5 valence electrons. Okay, well, we just said that this one needs to go away, so it does. But so that magnesium's happy, that magnesium's happy. But this one still needs 2 more. Where could it get 2 more? You got it. Another magnesium. So now those 2 leave and come over here. And now look, and rewind the video if you have to. How many magnesiums do we have? We have 3 magnesiums. How many phosphorus do we have? Oops. How many phosphorus do we have? We have 2. But isn't it a lot easier to just see that magnesium has a +2 charge, phosphorus has a -3 charge, and then go through the flow chart and end up at the bottom where you drop and flip and say Mg3P2. We get the same answer, but instead of going through the Bohr model and all these dot structures, all we have to do is say, okay, that's got a +2 charge, that has a -3 charge, but here's why this all happened.